Hello everybody, welcome into another lesson. So we finally have the worst part of taking derivatives behind us, at least for now. We've talked about the limit definition of the derivative of a function. Now we're finally on to some shortcuts. Today we are going to talk about the power rule for derivatives, as well as some sum and addition formulas for derivatives, and also the constant multiple rule for derivatives. But first, I think it would be helpful if we talked about some common derivative notations. Of course, what we've been dealing with for the past couple of lessons is f prime of x, meaning the derivative of the function f of x. Another notation you may see is y prime. That's if you have y equals some function of x, y prime's another notation for the derivative. You also may see dy over dx. What does that mean? What does dy over dx mean? It means the derivative of the function y with respect to x. That's exactly what that means. So the dy is the derivative of the function y with respect to x. All three of these mean the exact same thing, and you'll see all three of these used interchangeably. So f prime of x equals y prime equals dy dx. They all mean the exact same thing, so you'll want to get used to seeing all three of those notations interchangeably. Now let's get into what you really came for today, the power rule for derivatives. And this is going to make your life so much easier. So let's say let's bring out the power rule first. The power rule states that if you have f of x equal to some function of x raised to the n power, the derivative f prime of x is then equal to bringing down that power of n in front, multiplying it by the x raised to the n minus 1 power. So if you have x to some n power for your function f of x, to find the derivative, you'll take that n power, bring it down in front of your x, multiply it by the coefficient on x, and then you'll take your x and lower it by 1 degree. That's all the power rule states. First, let's do some real easy ones here. Let's get into some positive powers. So let's say I have f of x is equal to x squared. If I want to find the derivative of that, f prime of x, that is going to be where I take that 2, bring that down in front, multiply it by x, and then lower that power of x by 1 degree. I would get 2x to the first, or simply 2x. So the derivative of f of x equals x squared would be f prime of x equals 2x, based on that formula. And the power rule means we don't have to use that limit formula anymore. We have shortcuts. Let's do another couple of these. So let's say I have f of x equals x to the third. Alright, so let's find f prime of x. So to find the derivative of x to the third, I'm going to take that power of 3, bring it down front, multiply it by x, and then lower that power of x by 1 degree, which would be to the second power. So f prime of x in this case would equal 3x squared. Let's do one more with a positive power. So f of x equals x to the 100th power. And especially if you have f of x equal to where x is equal to the 100th power, you're probably thankful we have the shortcut. Could you imagine trying to use the limit definition and have to use the binomial theorem to expand x plus h to the 100th power? That would be horrible. You'd be there probably for many hours, maybe even a whole day trying to do that. The shortcut formula says that f prime of x equals that power of 100 brought down in front, so that'd be 100 times that x, and then you lower that 100 by 1 degree, that'd be to the 99th power. So f prime of x would equal 100 times x to the 99th power. So see how easy that is for the power rule? So much better than using the limit definition. Now, let's say we just have f of x equals x. Let's do a linear one. Well, we know that's the same thing as x to the first, right? Let's find f prime of x. So f prime of x, that's going to equal my power of 1 brought down front times my x, and then that power of 1 lowered 1 degree to x being to the 0 power. Well, x to the 0 itself is 1, so f prime of x is going to equal 1. And that makes sense if you think about it, because f of x is the same as y equals x. Well, that coefficient of 1 on your x is your slope, that's your m. So if you have a linear function, the derivative is simply the slope. That's all it is. This ties into the idea, in fact, that derivative is slope itself. So the derivative of f of x equals x is just 1. Now, what about constants? Where does that come in? I could pick any constant I want. Let's say f of x equals 10. So f of x just equals that constant 10. Okay, so how's that going to work? So let's find f prime of x. Well, what do we know about 10? Isn't that the same thing as 10 times x to the 0? Because x to the 0 is 1. So according to the power rule for derivatives, we'll bring down that 0 times that 10 times that x, which would be raised to the negative first power since we lower the degree by 1, but 0 times anything is 0. So f prime of x in this case is going to equal 0. In fact, for any constant whatsoever, let's say I pick f of x equals negative 2, then f prime of x is going to equal 0. Any constant at all, the derivative is 0 automatically. Let's say I pick g of x equals 0 itself. Well, the derivative of 0 is going to be 0. So g prime of x would also equal 0. Let's say I take h of x equals pi to the 30th power. Some people tend to treat pi as a variable, but it's not. We know pi is a constant, right? Raised to the 30th power. Well, it's still a constant, so h prime of x would equal 0. Because pi to the 30th is a constant, let's do k of x equals log base 5 of 2. Well, log base 5 of 2 is still a constant, right? It's going to be a hideous decimal, but it's still a constant nonetheless. That means that k prime of x is going to equal 0. And the derivative of any constant function is always 0, which comes from the power rule. So that's going to help us out too. Now, what about negative powers? It works just as well for negative powers. Let's say I take f of x. Let's say, for example, f of x equals 1 over x. So f of x equals 1 divided by x. Well, that's the same thing as x to the negative first. Sometimes it helps to rewrite this to a negative power, and then you can just apply the power rule. There's also a method coming in a few lessons called the quotient rule, which we could have used, but it's a much longer way to work with than what we're using here. But we can say f of x equals 1 over x, which is the same thing as x to the negative first. To find f prime of x, not f inverse, holy cow, I'm not doing an inverse function. Why am I saying that? F prime of x, we'll take that power of -1, bring it down front of the function, and then you'll lower that -1 by a degree. You would end up with negative x to the negative second, which could be simplified into -1 over x to the second. That would be your derivative. So this does work for negative powers. Let's do a couple more. Let's say I do 1 over x to the third. So I have f of x equals 1 over x to the third. I definitely want to find f prime of x, but what might help me first is to write that 1 over x to the third as an x to the negative power. So this would be the same thing as x to the negative third power. Now to find the derivative, I'll bring that -3 down front, multiply it by my x, and then lower that -3 by 1 degree. That would be to the -4th. -3x to the -4th is the exact same thing as -3 over x to the 4th. And that would be f prime of x. That would be my derivative. Alright, so those are for negative powers. Heck, let's do one more. Let's say I do 1 over x to the 100th power. So I'm going to find f prime of x, where I'm given f of x equals 1 over x to the 100th. It might be helpful to write this as x to the -100th power. Well, now to find the derivative, bring that power of -100 down front, multiply it by your x, and lower that -100 by 1 degree. This would become to the -101st power. So you get -100x to the -101st power, which should give you -100 over x to the 101st power. That would be your derivative of the function. You get -100 over x to the 101st power. So it works very well for negatives. Now you may be wondering, is there a function that just gives you 1 over x or x to the -1st as a derivative? Yes, the natural log function actually does that, but we're not going to do that until a few lessons from now. We're not doing the derivative of log functions today. That'll be a few lessons from now. Of course, the power rule also works if you have rational powers, such as, let's say, f of x equals the square root of x. We want to find the derivative of the square root of x. So we want to find f prime of x. Well, we know the square root of x itself, isn't that the same thing as x to the 1/2? So let's take x to the 1/2. Well, that's going to be then, if we take the derivative, we'll bring that 1/2 down front. This will become 1/2 times x, and then we'll lower that 1/2 by a whole degree. 1/2 minus 1, that's -1/2. Which is the same thing as 1 over 2 times x to the 1/2, which if we want to put it back in radical form, this would be the same thing as 1 over 2 times the square root of x. So the derivative of the square root of x is going to be 1 over 2 times the square root of x. Let's do a couple more rational powers. Let's say I do f of x equals the cube root of x. So we have f of x itself is equal to the cube root of x. This might help us to write it as x to a rational power, which would end up being x to the 1/3 power. Now let's find f prime of x. Well, in order to find f prime of x, bring that 1/3 down front times your x, then lower that 1/3 by a whole degree. Well, 1/3 minus 1 is -2/3, which sometimes you can leave your answer like this. Sometimes, though, it may be helpful to write it as 1/3 times x to the 2/3. Or for one more step, you could put this back into radical form. You would end up getting 1/3 times the cube root of x squared. So 1/3 times the cube root of x squared would be your derivative of the cube root of x. Let's do another power. And then we're going to go on to some sum and addition rules. Let's say I take f of x equals the 7th root of x. So I want to find the derivative of f of x equals the 7th root of x. Well, the 7th root we know is the same thing as x to the 1/7 power. Now let's go ahead and find the derivative. Let's find f prime of x. Well, I'll bring that 1/7 down front, multiply it by x, and then lower that 1/7 by 1 degree. Well, 1/7 minus 1, that's -6/7. So you would end up with 1/7 x to the -6/7 power, which is one way you can leave it. Or you can write this as 1/7x to the +6/7 power. Or if you want to put it back in radical form, you would end up getting 1/7 times the 7th root of x to the 6th power. Any of these three forms would suffice. It really just depends on how your professor wants it. But any of these three forms would suffice. I'm going with 1/7 times the 7th root of x to the 6th because, in my opinion, that looks cooler. But you could write it any of these three ways. If you were in my class, you could. Alright, so we've seen basic how do these powers work. Now let's come up with a few useful rules here. Let's say you have a constant times some function of x. Well, to find the derivative, if we take the derivative with respect to x of a constant times that function of x, that is simply equal to the constant times the derivative. That's all that is. Much like with a limit, if we're taking the derivative of a constant times some function of x, so the derivative with respect to x of a constant times f of x, that's the same thing as the constant times f prime of x, or a constant times the derivative of the function. So I'll do a couple of easy ones here. Let's say I have f of x is going to be equal to 4x to the 3rd. So what I could do then, if I want to find f prime of x, I would end up taking f prime of x to be, I would have that 4 times my derivative of x to the 3rd. Well, the derivative of x to the 3rd, I bring that 3 down front, multiply by x, and lower that power of 3 by 1 degree. Well, that would end up being x to the 2nd, and now I just multiply the result. I'll end up getting f prime of x equals 12x squared. So that would be my final answer for the derivative, would end up being 12x squared. All I got to do is take that constant multiple of 4 times the derivative of x cubed, and then I have the total derivative. Let's do one more. Let's say I do f of x equals 50 all over the 4th root of x to the 3rd. That one looks like a doozy, doesn't it? F of x equals 50 all over the fourth root of x to the third. Well, what might help us first is to write this as a power. We know 50 over x over the fourth root of x to the third, that's the same as 50 divided by x to the 3/4, which would be the exact same thing as 50x to the negative 3/4. Alright, so this would end up being 50x to the negative 3/4. Well, now we can do the derivative. F prime of x, that's going to equal that constant multiple of 50 itself, times, now we'll just deal with the x to the negative 3/4, bring down that negative 3/4 in front, multiply by x, and then lower that negative 3/4 by 1 degree. So negative 3/4 minus 1 is x to the negative 7/4. Well, we know 4 and 50 have a common factor of 2. So this would become 25 times negative 3 over 2, which would really give you negative 75 over 2 times x to the negative 7/4, which might help us in the fact that we're going to have negative 75 over 2 times x to the positive 7/4. Well, negative 75 over 2 times x to the 7/4. I mean, you could leave it this way, but I'm trying to write it in radical form. So this would be negative 75 over 2 times x to the 4/4. The reason I'm times x to the 3/4. The reason I'm separating these, okay, because 7/4 is greater than 1, we can separate these because x to the 4/4 is just x to the first, then you'll have x to the 3/4. If you want to write it in radical form, which some professors may want you to do, this would be negative 75 over 2x times the fourth root of x to the third, when you simplify this into radical form. Any of these three forms would work, but if your professor is insistent that you write it in radical form, negative 75 over 2 times the fourth root of x to the third is the answer you want. But you could leave it negative 75 halves x to the negative 7/4. That also works. So that's how you can apply the constant multiple rule with derivatives. And now, for the last segment, we're going to talk about sum and addition rules for derivatives. Let's say in total I have h of x is equal to some function f of x plus g of x. So h of x, of course, is just the sum of two functions together, f of x plus g of x. If I want to find the derivative h prime of x, all that is the same thing. It's going to be f prime of x plus g prime of x. So if you want to find the derivative of the sum, it's just the same thing as the sum of the derivatives. That's all the addition rule is. So the derivative of the sum of two functions, or more functions than that, you can apply it to more than two functions. The derivative of the sum of the functions is the same thing as the sum of their derivatives. Real easy. And of course, we can also do the same thing with differences, because basically addition is just the opposite of subtraction. Subtraction is just opposite addition. So if I want to find the derivative of the difference of two functions, it's just the difference of their derivatives. That's all that is. So let's do some examples of that. All right. Let's say I have f of x equals x squared plus 3x minus 4. So we got this function here, f of x equals x squared plus 3x minus 4. So to find f prime of x, I can use the sum and difference formulas. That's going to equal my x squared prime plus my 3x prime minus that 4 prime. Well, the derivative of x squared, that's going to be 2 times x to the first, or 2x, plus if I take the derivative of 3x, that's just going to be 3, and then minus the derivative of 4, that's 0. So my derivative would just become 2x plus 3. Using the sum and difference of derivatives, f prime of x is just going to be 2x plus 3. That's the derivative of the function. Let's do another. I have f of x equals 5x to the 8th minus 2x to the 5th plus 6. So I have the original function f of x equals 5x to the 8th minus 2x to the 5th plus 6. Well, actually, you know what? Let's change it from f of x to y. We're going to use y equals 5x to the 8th minus 2x to the 5th plus 6. Though f of x means the same thing, I just want to show you y prime. If we want to find the derivative, we could say y prime then equals the sum and difference of the derivatives of each of these terms. So y prime, that's going to equal the derivative of 5x to the 8th minus the derivative of 2x to the 5th plus the derivative of 6. Well, the derivative of 5x to the 8th, if I bring that 8 down front, multiply it by 5 times x, I would end up getting 40x, and then lower that power of 8 by 1 degree, that would be to the 7th, minus, let's take the derivative of 2x to the 5th. Well, I'll bring that 5 down front, multiply it by 2x, that would give me 10x, and then lower that power of 5 by 1 degree, that'd be to the 4th, plus the derivative of 6, a derivative of any constant is 0, so that would make y prime equal to 40x to the 7th minus 10x to the 4th. So there is my derivative. It's going to be 40x to the 7th minus 10x to the 4th. It's in the y prime form, so that means the same thing as f prime of x, but you also want to get used to seeing y prime. Let's do another here. Let's say y equals 1/2 of t to the 6th minus 3t to the 4th plus 1. Y is the same as f of t, of course. Well, that's fine. It doesn't matter what variables you use, as long as you know that y is the function of t. Let's use the y prime notation again. So y prime, the derivative, that's going to equal then the derivative of this 1/2 of t to the 6th minus the derivative of this 3t to the fourth plus the derivative of 1. Well, now find the derivative of 1/2 t to the sixth. I'll bring that 6 down front, multiply it by 1/2 t. 6 times 1/2 is 3, then times t. Lower that 6 by 1 degree, that goes to the 5th power. And then minus the derivative of 3t to the fourth. Well, bring that 4 down front, multiply it by 3, you get 12 times t. This would be 12t, and then lower that 4 by 1 degree, so 12t to the third, plus the derivative of 1. Derivative of any constant is 0. So y prime ends up being 3t to the fifth minus 12t to the third. That would be your derivative, would be 3t to the fifth minus 12t to the third. All right, let's do a couple with the dy dx notation. I'll show you how that works. So y equals, let's see. Y equals x squared plus 1 over x squared. So of course we want to find the derivative. Sometimes using dy dx notation is very nice. How are we going to use that to find the derivative? Well, each piece you're going to take the derivative of with respect to x. What does that mean? If I take the derivative of that y with respect to x, so I'm taking the derivative with respect to x, that's what that d over dx means. That's going to be equal to taking the derivative with respect to x of x squared plus the derivative with respect to x of that 1 over x squared, which we know is the same thing as x to the negative second, right? That might help us. Now, what do we do once we have the d dx notation? Well, the derivative of y, okay? Pretend for a second that's x instead. If we have the derivative of x to the first, that's just 1, right? So you would end up getting 1. Now, that y itself is a function. That's not the variable you're taking the derivative of. So you start out treating that y like the variable. You would take the derivative of a variable to the first power, but then you also have to consider that y is a function. So this would be 1 times dy dx, because that means you're taking the derivative of y with respect to x. That's going to equal, well, the derivative with respect to x of x to the second, that's just the derivative of the term. That would just be 2x plus the derivative with respect to x of x to the negative second. That would end up being negative 2 times x to the negative third. Well, 1 times dy dx, that's just dy dx. That's going to equal the right-hand side, which would be 2x. And then this would simplify into minus 2 over x to the third. So you'll end up getting that dy dx equals 2x minus 2 over x to the third. That's how this dy dx notation works. We took the derivative of the function y with respect to x. That's what that means. Let's do one more example, then we'll be done with the lesson. So, y equals x squared plus 4x plus 3 all over the square root of x. So we have y equals x squared plus 4x plus 3 over the square root of x. It actually might help us before we even try to differentiate this. Taking the derivative is called differentiation. That's where I'm using that term. But before I try to differentiate this function, I may want to simplify the original function here, right? Isn't that the same thing as x squared plus 4x plus 3 divided by x to the 1/2? That's the exact same thing. Now we can just do some simple exponent operations. You would end up getting that y itself would equal, if you take x squared over x to the 1/2, well, you would just subtract the powers. 2 minus 1/2, that's 4 halves minus 1/2. That would give you x to the 3 halves. So y would equal x to the 3 halves plus, you have 4x over x to the 1/2. Well, x to the first is the same as x to the 2 halves minus 1/2. That would end up giving you 4x to the 1/2. And then you'd have plus 3 over x to the 1/2. That would just be plus 3x to the negative 1/2. So now we've written this function in a simpler way to help us apply the power rule. So let's go ahead and do that here. So we want to find the derivative of this function with respect to x. So we're going to take the derivative with respect to x of y, set that equal to the derivative with respect to x of x to the 3 halves plus the derivative with respect to x of 4x to the 1/2 plus the derivative with respect to x of 3x to the negative 1/2. Well, now of course what we're going to do again is treat that y like it's the x variable temporarily. The derivative of y would just be 1, but 1 times anything is itself, but now we have to deal with the fact that y's the function, not the variable itself. Y's the function, so this would just become dy dx. The derivative of y with respect to x is going to equal the derivative with respect to x of x to the 3 halves. That would equal 3 halves times x. Then subtract 1 from 3 halves, that'd be x to the 1/2. Plus the derivative with respect to x of 4x to the 1/2. Well, that's going to be 1/2 times 4, which is 2, so that'd be 2 times x. And then you have 1/2 minus 1, that's going to be negative 1/2. Plus, you take the derivative with respect to x of 3x to the negative 1/2. Well, negative 1/2 times 3, that's negative 3 halves. And then you have, let's see, times x to the, if you lower negative 1/2 by 1 degree, that'd be to the negative 3 halves. So let's simplify this a bit. So 3 over 2 times x to the 1/2, that's the same as 3 times the square root of x over 2 plus 2x to the negative 1/2, that's the same as 2 over the square root of x. And then we have plus negative 3 halves, that'd be minus 3 over 2. Well, x to the negative 3 halves can move to the denominator and become positive. That would be negative 3 over 2x to the positive 3 halves, which is really the same as x times the square root of x. So in this case, your derivative, dy dx, is going to end up equaling 3 times the square root of x over 2 plus 2 over the square root of x minus 3 over 2x times the square root of x. So that's it for the power rule and those sum and addition rules and constant multiple rules that go with it. And now hopefully you also have a good feel for the notation of the derivatives and how that dy dx business works. The next lesson we're going to talk about the derivatives of absolute value functions and piecewise functions. So I hope everybody has a great day. Take care.